Hello? We now begin one of the most important transitions in this course. We move from the physical foundations of circuits, the conservation of charge and energy, to the mathematical methods we use to analyze and solve them. But as always, I want you to understand why these methods work, not just how. We are going to build nodal and mesh analysis from the ground up, starting with physics and ending with real examples. At the heart of every electrical circuit is a balancing act. At each node, charge must be conserved. Around each loop, energy must be conserved. And that gives us equations, simultaneous constraints that must be solved together. In other words, a circuit is not just a collection of wires and components. It's a physical system of interdependent conditions shaped by field theory and charge behavior. To solve such systems, we use nodal analysis based on Kirchhoff's current law and mesh analysis based on Kirchhoff's voltage law. Let's now build these methods from first principles. A node is not just a connection point, it's a junction for charge flow. Let's go to the atomic scale. At a node, free electrons arrive and depart. If more arrive than leave, net charge builds up, which creates an electric field that pushes back. But in a steady-state DC circuit, nature quickly counteracts any buildup. That's why we assume summation all the I at every node is equal to zero. This is Kirchhoff's current law derived from the continuity equation, which round rho over round t plus gradient of J is equal to zero. In steady state, round rho over round becomes zero. This reduces to gradient of J equal to zero. So KCL is just a restatement of charge conservation. In nodal analysis, we focus on voltages. Why? Because current through any component can be written as a function of voltage difference. I is equal to V of I minus V of J divided by R. So if we know the voltages at each node, we can find all currents. Let's talk about the procedure of nodal analysis. First step is to choose a reference node or ground, then label unknown voltages at other nodes. After that, we apply KCL at each non-ground node, and then express each current using Ohm's law. At the end, we solve the resulting system. Let's walk through an example. From the circuit schematic, we know that the source voltage is equal to 10 volts, and it is connected between node A and ground. Resistance 1 is 1 ohm, and it is between node A and node B. Resistance 2 is 2 ohm, and it is between B and ground. Resistance 3 is 3 ohm, and it is between A and ground. Let's find the voltage at node B. We know voltage of node A is 10 volts, and voltage of ground is 0. If we apply KCL at node B, we see that 10 minus voltage of node B divided by 1 ohm is equal to voltage of node B divided by 2 ohm. Therefore, we can solve the equation for voltage of node B, as you can see the process in the video. The result is that voltage of node B is equal to 6.67 volts. What we get from these process? The intuition behind this process is node B balances current inflow from node A and outflow to ground. The 6.67 volts result reflects a compromise between the high potential at node A and the zero at ground, shaped by resistance ratios. KCL ensures no net charge builds up. The flow in equals the flow out. Now let's look at loops. When a charge moves around a closed loop, the net work done must be zero. That's because the electrostatic field is conservative, meaning the integral EDL over a closed loop is equal to zero. This gives us Kirchhoff's voltage law, which indicates that summation of all the V is equal to zero. So every voltage rise from a source must be matched by drops through resistors or other loads. KVL is nothing more than energy conservation in a closed circuit. In mesh analysis, we focus on loop currents. We assume one current per loop and apply KVL to each loop. To run the mesh analysis, we have to follow the following procedure. First, identify all meshes. Then assign a current to each mesh, which is usually clockwise. After that, we apply KVL around each loop. Remember, for shared elements, current is the difference of mesh currents. At the end, we solve the system. Let's consider a two-loop circuit with two voltage source, like you see in the image. Left loop includes a voltage source equal to 12 volts connected to a 2 ohm resistance. Right loop includes a voltage source equal to 6 volts connected to a 4 ohm resistance. Both loops shared a 1 ohm resistor. Let's assume that I1 is the left loop current and I2 is the right loop current. Conducting a KVL over loop 1, we will see that 12 volts minus I1 times 2 ohm minus differences of both current times 1 ohm is equal to 0. In the right loop, we see that 6 volts minus I2 times 4 ohm minus differences of the currents times 1 ohm become equal to 0. Now, from the first loop, we can find I2 based on I1. So we see that I2 is equal to I1 times 3 minus 12. Plug it into the equation that we have for the second loop, we will see that I1 is equal to 4.714 amp. We already know how to find I2 from I1, so we will find out that I2 is equal to 2.143 amp. Let's see what it told us. First of all, the shared resistor carries the summation of currents. Also, each loop balances voltage rises and drops. So no energy is created or lost, which KVL ensures about this. But how do we decide which method we have to use? We use nodal analysis when we have fewer nodes or circuit has many resistors connected to ground, and the main goal is to solve for voltages. We use mesh analysis when we have planar circuit and loops are clearer than nodes or we have many voltage sources. So what did we really do? We started with Newtonian physics and field theory. We saw how KCL comes from charge conservation and KVL from energy conservation. Then we built two powerful tools. The nodal analysis, which is good for solving for voltages using KCL, and the mesh analysis, which is good for solving for currents using KVL. And through examples, we saw these methods in action, not just mathematically, but physically. Every time you solve a circuit, you are solving how nature balances itself, ensuring charges don't pile up and energy isn't lost. These methods are not just computational, they're deeply expressive of the physical world.